Far across the Milky Way there shines a star so luminous it could outshine millions of suns, Cygnus OB2-12. What makes this colossal blue supergiant burn so intensely, and how long can it survive? Tonight, we'll uncover the secrets of one of the galaxy's brightest stars. If you enjoy cosmic journeys, please like, subscribe and share, and tell us in the comments which star in the universe fascinates you the most. Thank you for watching. Now, let's begin. The view begins far from any single object along a long corridor through the disk of the Milky Way toward the constellation of Cygnus, where the star fields thicken and the night becomes a crowded fabric of light. This corridor is not empty. It is a layered medium that mixes gas and dust, and every photon must cross those layers before it reaches an instrument. Starlight travels through cold clouds and warm intercloud regions, through ionized cavities inflated by massive stars, and through lanes of dust that thread the spiral arm like faint braided rivers. The result is a sky that glows with countless points, yet hides much of its true brightness behind a shifting veil. Extinction, the dimming and reddening caused by dust grains, defines the first impression here. It removes more blue light than red, so objects that are intrinsically blue can appear much redder and fainter than they are. In this direction, the extinction is not uniform. It varies from one small patch to the next, and that variation makes colours and brightness uncertain until the veil is measured with care. The corridor also lies close to the midplane of the galactic disk where most gas and dust reside, so crowding becomes the second defining fact. Many stars occupy even a small field, and their profiles can overlap if the angular resolution is not high. Space-based observatories ease that problem by delivering sharp images, yet they do not thin the sky. They only separate the lights more cleanly. Because the interstellar medium along this path is structured, different wavelengths reveal different depths. In visible light, the densest clouds appear as dark lanes and patches that break the star field into clumps. In the near-infrared, many more stars appear, because longer wavelengths slip past the dust more easily, and the crowding intensifies. In the mid-infrared, the warm dust itself glows along the rims of cavities and the edges of clouds, drawing glowing outlines around the shapes carved by radiation and winds. Radio observations trace the cold molecular gas through the emission of specific molecules and show long filaments and knots that remain hidden at shorter wavelengths. These multi-wavelength views together define the far-field context, a busy spiral arm where star formation is common and where young hot stars share space with older populations lined up at many distances. The phases of the interstellar medium also reveal themselves along the way. Cold molecular gas collects into elongated clouds opaque to visible light, yet translucent in the infrared, and it provides the raw material for new stars. Warm atomic gas fills the spaces between molecular complexes and glows softly in emission lines excited by ultraviolet radiation. Hot, ionized gas marks the interiors of cavities formed by stellar winds and past explosions, giving the corridor a foam of low-density bubbles whose walls are brighter and denser. Pressure balance among these phases is approximate, so boundaries ripple under the push of radiation and turbulence, and structures change slowly with time. Feedback from massive stars leaves recognizable signatures. Radiation pressure pushes on dust and heats, gas carving low-density paths. Winds drive supersonic flows that sweep up shells and arcs around their sources. Shock waves compress clumps that may later collapse into new stars, and pillars rise where dense knots resist erosion. When viewed from far away, the network of cavities, arcs, and filaments records the recent history of energy input and provides landmarks that guide interpretation. Distance estimates in this direction require patience. Trigonometric parallax, the gold standard that measures tiny apparent shifts as Earth moves around the Sun, is complicated by the crowded dusty field because faint targets are hard to measure and reference frames can be tangled by blending. Photometric methods which compare observed brightness and colour with model atmospheres depend on accurate extinction corrections and on knowledge of how the extinction changes from place to place. Spectroscopic parallax, which uses spectral type and luminosity class to infer an intrinsic brightness, and then compares it with the observed brightness, inherits the same dependence on extinction and adds sensitivity to classification. For these reasons, published distances to objects along this corridor can differ, and careful work combines multiple methods and many bands to reduce the spread. The same conditions that challenge distance also challenge the measurement of intrinsic brightness. A star viewed through heavy reddening can seem modest until corrections are applied, and those corrections must respect the exact shape of the dust law along this line of sight. Polarization measurements add a further tool. Aligned dust grains preferentially transmit light with a particular orientation, so polarization maps reveal the directions of magnetic fields that thread the medium, and those fields in turn influence how clouds are shaped and how filaments are drawn. The far-field picture is therefore a synthesis. Photometry gathers colors across the spectrum to separate temperature from reddening. Spectroscopy reads the fingerprints of atoms and ions to identify hot stars and to map the state of the gas. Polarimetry traces the grain alignment and the magnetic scaffolding. Interferometry in the infrared sometimes resolves faint halos around luminous stars, while high-resolution spectroscopy resolves wind-shaped line profiles that betray motion in the outer layers of the brightest sources. Each technique applied to the same corridor reveals a different slice of depth and structure, and together they turn the crowded field into an organized set of layers rather than a flat tapestry. In this orientation, the goal is simple and disciplined. Establish the path through which light must pass, and the filters that the galaxy imposes. Recognize that the corridor magnifies opportunity by gathering many massive stars into one vista, while also magnifying difficulty by hiding their true light behind dust and by stacking many distances along a single line. Accept that no single wavelength is sufficient, and that no single method is decisive. The way forward is to measure extinction carefully, to handle crowding with sharp images and cautious photometry, and to combine information across bands so that the veil can be lifted without tearing the fabric of the data. Only then does the corridor yield a reliable background against which any exceptional object can be located and studied. The far-field frame is in place, a dense, veiled and luminous reach of the Milky Way, where bright, hot stars shape their surroundings, and where any individual source must first be understood as a beam that has travelled through this complicated medium before it arrives. The corridor narrows into a named landscape known to radio maps, infrared surveys and optical plates as the Cygnus X star-forming complex, a wide expanse within the Cygnus arm, where gas and dust collect in massive reservoirs, and where the imprint of hot young stars becomes the dominant sculptor of shape and light. A star-forming complex is a region that contains large clouds of cold molecular gas, warmer atomic layers, and volumes of ionized hydrogen, which is hydrogen stripped of its electrons by strong ultraviolet radiation. In this setting, all three phases are present together in adjoining layers that wrap around clusters and cavities. The coldest material organized into giant molecular clouds is traced by the emission of molecules such as carbon monoxide, which acts as a stand-in for molecular hydrogen that is otherwise difficult to see. These clouds run in long filaments and knots, many tens of light years in length, with dense clumps along their spines that can collapse into new stars. Between and around these cold structures sits warm atomic gas that has been partially heated and agitated by radiation and by flows, and beyond that, closer to the most luminous stars lie ionized hydrogen regions, bright volumes where ultraviolet light maintains a continual state of ionization, and where the gas emits characteristic lines as electrons recombine. Feedback, a word used to describe how stars alter the medium that made them, appears everywhere in this complex winds. From massive stars sweep up expanding shells. Radiation erodes cloud surfaces and carves pillars that point back toward the energy sources. Supernova remnants from previous generations stir shock fronts that run through the clouds and leave ripples that can compress gas and seed new collapses. The result is a foam-like network of bubbles and ridges, a pattern seen clearly in radio and infrared images, where the glow of heated dust picks out the walls of cavities like contour lines on a map. Embedded within the complex are clusters at different stages of development, from deeply veiled groups still cocooned in their birth clouds to exposed associations dominated by hot O-type and B-type stars, whose combined radiation fields create wide ionized volumes. O-type stars are the hottest and most massive common stars, and B-type stars are slightly cooler but still hot and luminous. Together they define the ultraviolet climate of the region, setting the ionization fronts, the boundaries where neutral gas becomes ionized, and pushing those boundaries outward as long as their light remains strong. The geometry is layered yet not symmetric because density varies across the clouds, and the advancing fronts find paths of least resistance, leaving arches, chimneys and blowouts where low-density channels allow hot gas to vent into larger volumes. Radio continuum maps reveal the ionized interiors, while spectral line maps at radio wavelengths reveal the cold clouds that form the walls. Mid-infrared images sensitive to warm dust and to specific molecules that shine, when excited by ultraviolet photons, draw bright filigree along the rims of these same structures. Optical images show where dust lanes are thin enough to admit visible light, and where glowing edges face the high energy sources, but much of the complex remains optically faded by foreground extinction, making the infrared the primary tool for counting embedded stars. The complex also carries signs of sequential star formation, a process in which one generation's feedback compresses nearby gas and triggers the next generation in adjacent layers, though the timing and causality must be established carefully with age dating rather than assumed from morphology alone. Age spreads within clusters, and across the complex are measured by placing stars on diagrams that relate colour to brightness, and comparing their positions to tracks predicted by models of stellar evolution. In the infrared, these diagrams remain useful even through heavy dust. Kinematics add another dimension to the picture. Spectral line profiles of molecules in the clouds record motions along the line of sight, revealing converging flows where filaments meet, and expanding signatures where shells move outward. Ionized gas lines trace flows within cavities and along bright rims, and sometimes show the fingerprints of turbulence where wind shocks and radiation pressure interact with uneven boundaries. Combine these velocity measurements turn still images into living structures, with expanding, collapsing and shearing components that obey conservation of momentum and respond to pressure differences among phases. Magnetic fields thread the complex as well. Polarization of starlight and of dust emission reveals field orientations which tend to align with long filaments in cold gas, and to resist compression perpendicular to the field lines, thereby influencing which directions collapse more easily. The presence of magnetic support changes the threshold density needed for gravitational collapse in a given parcel, and can guide accretion flows along preferred paths toward forming clusters. Cosmic rays and far ultraviolet photons set the chemistry in cloud surfaces, creating photodissociation layers, where molecules are broken and reformed in a steady dance controlled by radiation strength and density. And these layers regulate how cooling proceeds by controlling which lines can radiate away energy. The scale of the complex means that many observational beams, even those from sharp instruments, sample populations rather than single objects. So derived properties such as average density temperature or radiation field strength must be interpreted as distributions rather than uniform values. Despite these complexities, the Cygnus X complex serves as a clear outer stage for any single bright star within its bounds, because it defines the prevailing conditions, high radiation fields from hot associations, a patchwork of high and low, column densities of dust, a web of shells and filaments that affect how light and wind propagate, and a history of overlapping generations that leave their expanding signatures in gas and dust. In this environment, even a single luminous source does not act in isolation. Its wind and light add to the shared pressure budget and find their way preferentially along pre-existing channels, while its measured spectrum and brightness are filtered by the same dust layers that cover the entire view. Instruments tuned to multiple wavelengths disentangle these effects by separating emission from ionized volumes, reflection from dust grains, thermal emission from warm grains, and line emission from cold molecules, and by matching features across bands, they recover the three-dimensional arrangement of shells and clusters. Because each tracer responds to different densities and temperatures, the combined set builds a consistent physical model in which the cold phase supplies mass. The warm atomic phase mediates energy exchange, and the hot ionized phase marks the active inner surfaces facing the dominant radiation sources. With this model in hand, the complex becomes less a maze and more a readable map, one that shows where clusters have formed, where energy is injected, and where material accumulates. The Cygnus X complex therefore stands as the natural outer frame for the study of any exceptional star within its bounds, providing the context of raw material radiation turbulence and magnetic structure that shape observations and that set the boundary conditions for the immediate surroundings of luminous objects deeper inside. Attention moves inward from the wider complex to the Cygnus OB2 association, a loose yet massive congregation of hot young stars that rules the local radiation field and sets the dynamical weather for tens of light years. An association is a gravitationally unbound or marginally bound grouping that forms from the same generation of clouds and then expands as internal motions carry members apart. In this case, the concentration of O-type and B-type stars indicates a recent epoch of formation and a high yield of massive objects. The stellar census uses multi-wavelength surveys because dust along the line of sight hides much of the optical light. Near-infrared catalogues recover hundreds to thousands of members whose colours corrected for reddening reveal a broad spread in mass with a strong luminous upper end. The most massive stars produce ionizing photons in large numbers and drive fast winds, and together they inflate overlapping cavities whose combined pressure sculpts the association's interior. Age dating relies on placing members on color magnitude diagrams and comparing their positions with model tracks for young populations. The results cluster around a few million years, with evidence for a spread of a few million years more, a pattern consistent with sequential pockets of formation within a common cloud complex. These ages place the hottest members still on or near the main sequence, the stage where hydrogen fusion in the core supports the star, while some less massive members approach later pre-main sequence phases where disks and envelopes fade. The spatial distribution of sources is clumpy with denser knots that align with residual dust structures and with evacuated lanes where winds have cleared channels, extinction varies strongly across the face of the association, so a single colour correction does not suffice. Maps of reddening are built from the colours of many stars and from infrared dust emission, and these maps show that some lines of sight are veiled by many magnitudes of visual extinction, while others are comparatively clear. Because extinction can mimic the colours of cooler stars, spectral classification is essential for the bright end of the population. Spectra of O-type and early B-type stars show helium and hydrogen features, characteristic of high temperatures and luminosity. Class indicators identify the most evolved giants and supergiants within the group. Radial velocities from the spectra and proper motions from precision astrometry establish membership more securely by separating association stars from foreground and background field populations that happen to lie along the crowded sightline. When astrometric data allow parallaxes to be measured, the mean distance of the association is derived with improved confidence, though individual uncertainties remain because reddening and crowding degrade some measurements. This distance, coupled with corrected photometry, sets the scale for intrinsic luminosities used in later steps. The association's internal kinematics reveal a modest velocity dispersion, a natural outcome for a young assembly that is not deeply bound and that still expands from its birth configuration. Gas that once filled the volume has largely been pushed aside, though molecular fragments survive along the periphery and within sheltered pockets. Ionized gas traces bright rims and surfaces that face the hottest stars, marking a three-dimensional boundary network where photons carve shallow layers into surviving clouds. The energy budget is dominated by ultraviolet radiation and by mechanical input from winds. Each O-type star carries a wind that leaves a signature in P Cygni line profiles, and in aggregate these outflows merge into a pervasive flow that vents through low-density corridors toward the larger cavities of the surrounding complex. The hot interiors of these cavities reach temperatures of millions of degrees Celsius, where shocked wind material accumulates, and although that gas is tenuous, its pressure supports the evacuated volumes and slows infall from surrounding layers. Within the association, evidence for mass segregation appears as the brightest and most massive stars cluster towards certain centers, though the degree to which this distribution reflects initial conditions or early dynamical evolution remains an open question that is addressed by comparing simulations with the observed radial profiles of star counts. The initial mass function, the statistical distribution of stellar masses at birth, appears broadly similar to that measured in other young regions, when biases from extinction and crowding are accounted for, although the high mass tail is well populated here because the region formed a large number of stars overall. This high mass content explains the strong ionizing field measured across the association, which in turn explains the presence of diffuse emission and of sharp ionization fronts along cloud interfaces. Because the association lies within a complicated layered sightline foreground, and background structures can imprint additional emission and absorption features on spectra and images. Distinguishing which features belong to the association requires careful matching of velocities and distances. Polarization patterns across the field trace magnetic orientations and show that the association sits within a magnetized environment whose field lines tend to follow large-scale filaments and arcs, and these fields influence how shells expand by favoring motion along some directions over others. Embedded low-mass stars provide another dimension of the population. Many carry disks in their earlier stages identified by infrared excesses that rise above photospheric emission at longer wavelengths. The fraction of disk-bearing members declines with age, so the measured disk fraction supports the inferred few million-year timescale. and indicates that planet-forming material still exists around a significant subset of the low-mass population, although the harsh radiation from nearby massive stars can erode the outer parts of those disks and shorten their lifetimes. X-ray observations detect numerous young low-mass stars through their hot coronae, allowing membership estimates independent of infrared colours and revealing concentrations that coincide with known subclusters. Together, these datasets produce a three-dimensional map in which hot luminous stars occupy partial cores. Lower mass stars spread more widely, and dust defines patchy screens that vary over small angles. The association's boundaries are statistical rather than sharp, defined by where star counts above the field level taper and where the common velocity pattern fades. On those edges, shells meet surrounding clouds and trigger thin layers of compression that sometimes host very young objects still deeply embedded and visible only at long wavelengths. The presence of such objects shows that star formation is not yet entirely finished, although the balance of mass has already moved into exposed populations. Radiation pressure and winds continue to modify the immediate environment, lifting small grains and pushing on larger ones, setting up drift that alters dust-size distributions and subtly changes the shape of the extinction curve from place to place. Observers correct for this by fitting multi-band photometry to flexible dust laws rather than assuming a single curve. With these ingredients assembled, the Cygnus OB2 association stands as a coherent inner stage, a young, massive and luminous grouping whose ultraviolet light fills a wide volume, whose winds excavate and pressurize cavities, and whose stellar content across masses and evolutionary states can be measured with a combination of spectra photometry and precise motions. It defines the immediate context into which any single luminous member must fit, sets the mean radiation and wind pressures that shape surrounding gas, and supplies the crowded backdrop through which line profiles, colours and fluxes must be interpreted with care. Dust governs what light survives the journey through this arm of the galaxy, and reddening the selective removal of blue light compared with red shapes every measurement in this field. Interstellar dust is not soot in a uniform fog. It is a mixture of tiny solid particles with sizes from a few molecules to fractions of a micron made of silicates, carbon-rich compounds, and ices where conditions allow. These grains both absorb and scatter light. Absorption converts photon energy into heat that later leaks away at longer wavelengths, while scattering redirects photons out of the original line of sight. Because smaller grains interact more strongly with shorter wavelengths, blue light is diminished more than red light, and a spectrum that begins as very hot can appear much warmer when it reaches a detector. The strength of this reddening is controlled by the column density of dust along the path, and by the size distribution of grains, which in turn depend on the local history of star formation, shocks and radiation. In regions filled with young hot stars, radiation can erode the smallest grains or change their coatings, while shocks from winds and past explosions can shatter larger grains into smaller fragments. As a result, the shape of the extinction curve the way. Extinction varies with wavelength, is not universal but varies from place to place. Observers describe this variation with a parameter that compares total extinction in visible light to the colour change between two bands, but even without naming that ratio, the practical point remains that one must measure colours in several bands to decide which curve applies along a given narrow line of sight. Dust is not evenly spread. It collects in filaments and sheets with sharp edges and holes, and these structures sit at different distances. The stacked arrangement means that two nearby stars on the sky can suffer very different reddening because their paths cross different parts of the foreground layers. This differential reddening complicates the interpretation of colour magnitude diagrams, because stars of the same type can appear along a slanted sequence rather than a tight line. To correct this, maps of reddening are built by sampling many stars and solving for the colour shift that best returns, each to a physically reasonable temperature. In clusters and associations, a subset of hot stars with well-understood spectra act as anchors because their intrinsic colours are predictable. Their observed colours then reveal the total colour excess caused by dust. When combined across the field, these anchor points sketch a two-dimensional reddening map. To lift that map into 3 dimensions, distances for many stars are matched with their individual reddening values, and the cumulative growth of extinction, with distance reveals where major dust layers sit. Such distance-resolved maps show that much of the visible dimming in this direction accumulates in 1 or 2 large steps associated with the star-forming complex, while additional layers contribute more gently beyond. The presence of dust also polarizes transmitted light. Many grains are elongated and tend to align with the local magnetic field, so they selectively transmit light with electric fields aligned along a preferred direction. This imprint allows the orientation of magnetic fields to be inferred and provides another check on which parts of the sky carry the heaviest dust loads. Polarization increases with the amount of dust up to a saturating level, so the pattern of polarization vectors across the field traces both density and geometry. These measurements complement infrared observations in which the dust itself emits. Warm grains glow in the mid-infrared drawing, bright outlines along ionized rims and cavity walls, while colder grains radiate at longer wavelengths that reveal the bulk mass of clouds and filaments. By comparing the brightness of this thermal emission with the extinction seen in starlight observers, calibrate dust mass and grain properties, ensuring that the dust law applied to stars matches the dust that radiates nearby. In practice, multi-wavelength fitting is essential. Photometry from the visible through the near-infrared and into the mid-infrared constrains the temperature of each star and the column of dust in front of it. Spectroscopy provides independent temperature and gravity indicators and reveals interstellar absorption features, including diffuse interstellar bands that correlate loosely with dust columns. The combination breaks degeneracies that would otherwise allow a cooler unreddened star to masquerade as a hotter reddened one. Crowd control is a separate challenge in a rich association because overlapping profiles can bias colors and brightenings. Sharp imaging and point spread function fitting reduce this bias, and cross-checks between space-based and ground-based catalogues identify blends that might otherwise go unnoticed. The physical consequences of dust go beyond color. Extinction reduces the observed brightness, so without correction a very luminous source can appear merely ordinary. Correcting requires a distance and an extinction law, both with uncertainties, and those uncertainties propagate into the intrinsic luminosity. Because the correction is largest at short wavelengths near infrared bands, often provide the most stable anchors for luminosity estimates in heavily veiled fields. They suffer less extinction and are less sensitive to small shifts in the dust law. However, near-infrared colours change less with temperature than visible colours, so classification relies more heavily on spectra in those bands. This trade-off explains why work in such regions uses both visible and infrared data, rather than choosing one domain. Dust also affects the gas around young stars by shielding molecules from dissociating radiation, and by providing surfaces where simple molecules meet and react. In cloud surfaces, far ultraviolet photons set up thin layers where carbon is singly ionized and where molecules like carbon monoxide are broken and reformed. Deeper inside dust blocks the radiation enough that molecules survive, and the cooling they provide allows collapse to continue. In ionized regions, dust absorbs a portion of the ionizing photons, and reduces the size of glowing volumes for a given stellar output, an effect that must be included when estimating the energy budget from radio and optical lines. Radiation pressure acting on dust grains can push material outward, clearing cavities around luminous stars and shaping arcs that curve away from the stronger sources. The dust size distribution can evolve within these flows because small grains are more easily accelerated and removed, leaving larger grains behind and altering the extinction law locally. Observers watch for these signatures when they map reddening across cavities and along rims. Finally, the presence of dust defines the observational strategy. To recover intrinsic properties for bright hot stars in this association, one identifies stars with reliable spectral classifications, measures multi-band photometry, fits a flexible extinction law, and solves for temperature reddening and distance together, subject to consistency with the wider field map. Where possible, interferometry and high-resolution spectroscopy probe halos, winds and line profiles that carry separate information on the outer layers and can be compared with models that include the effects of scattering and absorption. With all these steps, the dust veil becomes a measurable filter rather than an opaque obstacle. The resulting corrected colours and fluxes place each luminous source on a firmer physical footing, and the layered map of extinction provides a stable background for interpreting any bright, hot star embedded in the association that lies behind this complex network of grains and gas. Distance in this crowded reddened direction is both the most basic requirement and the most delicate quantity, because every intrinsic property that follows depends on it, and because several independent methods carry biases that become important when dust is heavy and the field is dense. Trigonometric parallax, which measures the tiny annual shift of a source as Earth orbits the Sun, stands as the most direct ruler, yet bright hot stars embedded in a complex background test the limits of astrometric precision. Crowding perturbs the measured centroid when faint neighbours blend within a point spread function, and variable nebulosity can shift backgrounds between visits. Heavy reddening forces reliance on longer wavelength astrometry, in which instruments may be less sharp and very luminous. Stars can saturate detectors in visible bands, complicating calibration. Space-based catalogues provide parallaxes for many association members, but the most luminous individual sources may carry larger formal uncertainties or quality flags that caution against adopting a single value at face value. Astrometric solutions also assume a steady photocenter. If a star has an unresolved companion or exhibits wind-formed halos that change subtly with time, the photocenter can wobble or drift, adding noise that masquerades as parallax and biasing the result. For these reasons, distance to a rich association is often estimated by combining parallaxes statistically across many secure members, rejecting outliers from blends or poor fits, and solving for a common mean that averages down individual errors. This approach also reveals the depth of the association along the line of sight, because the spread in corrected parallaxes exceeds formal errors when real structure extends over tens of parsecs. Spectrophotometric distances provide a second complementary ruler. A spectrum yields a temperature and a luminosity class. Coupled with model atmospheres and bolometric corrections, these define an intrinsic brightness. Comparing that intrinsic brightness with observed brightness across multiple bands and solving simultaneously for reddening and its wavelength dependence produces a distance estimate for each star. In fields where the extinction law varies, this approach must allow the curve to change from one sightline to the next, or else it will bake systematic errors into the distances. The strength of the method is that it applies to bright stars whose parallaxes are noisy or ambiguous. Its weakness is that it inherits all uncertainties from spectral classification model choices and dust law selection, and it can be fooled if a star's light includes significant emission from winds or circumstellar material that changes the apparent continuum or line profiles. Kinematic distances, which infer distance from radial velocity by assuming circular rotation of the galaxy, are of limited use in this sector because the geometric configuration near the solar circle yields small gradients of radial velocity with distance. Streaming motions within spiral arms, local turbulence in star-forming complexes, and winds from clusters further erode the link between measured velocity and distance, so velocities serve better to establish membership than to set a scale. Very long baseline interferometry can in special cases measure parallaxes to Massey spots in nearby star-forming regions, with exquisite precision anchoring a local rung of the distance ladder. Where such measurements exist within the same complex, they provide a firm reference for the broader structure, even if no masers trace the immediate environment of a particular bright star. Eclipsing binaries and resolved spectroscopic binaries add another geometric tool. When orbits are measured in both radial velocity and on the sky, or when eclipses yield precise radii and temperatures, distances follow with modest model dependence. In a crowded association, these systems are rare and challenging, but even a few anchors can calibrate the distance to the population. Bayesian inference ties these strands together. Prior knowledge of the three-dimensional distribution of stars in the disk of the extinction as a function of distance in this direction, and of the expected depth of the association enters as a prior, while parallax likelihoods and spectrophotometric likelihoods enter from the data. The posterior yields distances for individual members and for the ensemble, with uncertainties that reflect both measurement noise and population assumptions. This framework allows outliers to be downweighted and lets the analysis incorporate the fact that some astrometric solutions carry excess noise. It also handles the nonlinearity that turns small parallax errors into large distance errors at large distances. Practical work applies quality cuts to astrometric parameters to exclude solutions degraded by blending applies, 0-point corrections to parallaxes where required by instrument calibration, and cross-matches to infrared catalogues to ensure that the same objects are traced across bands. For the brightest hypergiants, even high-quality solutions may remain uncertain, and in those cases the safest course is to tie the star to the association mean distance, while propagating an uncertainty that includes the depth of the group and the local reddening structure. The consequences of distance uncertainty are straightforward and significant. Luminosity scales with the square of distance, so a fractional error in distance doubles when expressed as a fractional error in luminosity. When ranking the most luminous stars in the galaxy, such distance-driven uncertainty can move a source up or down the list without any change in its measured flux. The bolometric correction required to convert a color-based temperature into a total energy output also depends on temperature and on how the wind and outer layers alter the apparent continuum. If a blue hypergiant carries a dense, partially optically thick wind, then simplistic photospheric corrections can undercount or overcount the total output unless models include the wind. These model choices couple with distance to set the final luminosity band. Extinction interacts with distance as well. An overestimated extinction will inflate the inferred intrinsic brightness for a given flux, which can mimic the effect of pushing the object farther away. An underestimated extinction does the opposite. Resolving this requires simultaneous fits to distance and extinction across multiple bands anchored by spectral types that limit the allowed temperatures. The near-infrared offers a partial advantage because extinction is lower. They're reducing the size of the correction, but the leverage to separate temperature from reddening also becomes smaller. demanding higher quality spectra to maintain accuracy. Differential reddening inside the association introduces an additional spread in derived distances if a single extinction law is applied, a flexible law informed by maps of dust emission and by polarization where available reduces this spread and aligns the distances of hot luminous members more closely. Finally, hierarchical modelling that treats the association as a parent population with a mean distance, a physical depth, and a reddening distribution yields a consistent set of distances that respect both the shared environment and the local variations. With these tools, the distance to the association converges toward a value within a narrow range expressed in thousands of parsecs, while acknowledging a real depth of some tens of parsecs. A bright blue hypergiant within the group inherits that ensemble distance with an uncertainty that reflects both measurement limits and structure. That range, when carried forward, sets the scale for radius luminosity and wind power, and it frames all later steps that move from the environment to the immediate neighbourhood and then to the layers of the star itself. Massive neighbours fill the association like small suns within a shared sky, and their combined output sets the weather that every local parcel of gas and dust must endure. Each Hotto-type star pours a flood of ultraviolet photons that ionize hydrogen and keep large volumes in a charged state, while each fast wind expels matter from the stellar surface at thousands of kilometers per second and drives shocks into the surrounding medium. In a crowded association, these individual spheres of influence overlap, and the result is not a set of isolated bubbles, but a connected labyrinth where cavities join shells, collide, and pressure gradients steer flows along channels carved by earlier generations of energy input. The nearest neighbours to any luminous member matter because overlapping radiation fields increase the ionization parameter, the ratio of photon density to gas density, and that parameter decides the thickness of bright rims, the chemistry of cloud surfaces, and the cooling pathways available to shocked gas. When two winds meet, their ram pressures set a contact discontinuity, and along that surface a thin hot layer radiates in X-rays, while cooler layers condense farther out. If the winds are unequal, the surface bows around the weaker source. If they are comparable, the surface lies between them, and instabilities ripple along it as shear flows develop. In 3 dimensions, the network of such contacts fills the association with curved sheets, knots, and filaments that register where momentum is exchanged. Radiation adds a second pervasive push. Photons striking dust grains transfer momentum and accelerate the grains outward, and because gas couples to dust by drag, gas is drawn along too. The net effect is a slow, steady shove that hollows low-density zones near the brightest clusters and that sweeps dust into arcs, oriented concave toward the energy sources. Where cloud edges face strong illumination, photoevaporation flows stream away from the surface at a few kilometers per second, carrying mass into the cavities and feeding the hot interiors where winds and radiation mix. Those flows thin the edges until they can no longer shield the molecular interior, at which point the ionization front eats into the cloud and leaves pillars that point back toward the dominant stars. The scale of these features ranges from a fraction of a light year around single hot stars to many light years where subclusters act in concert. Because the association is young, supernovae have only just begun, or are still rare, so the dominant feedback comes from radiation and winds rather than explosions. Even without explosions, mechanical energy injection is large, and over the cluster lifetime it suffices to excavate cavities whose interiors remain overpressured compared with the ambient medium. The hot plasma inside these cavities cools slowly, so pressure equilibrium is reached not by rapid cooling, but by expansion that pushes on the surrounding shells. These shells in turn sweep up neutral gas and dust, compressing them into thin walls. Where two expanding shells meet, they pile gas into ridges that can become gravitationally unstable. In this way, feedback both destroys and creates. It erodes the natal clouds that once fed star formation, while it also sets up secondary sites where collapse can be triggered if conditions align. Observations show that the brightness of polycyclic aromatic hydrocarbon features, which trace small carbonaceous grains excited by ultraviolet light peaks along the illuminated sides of such shells, while molecular line emission peaks just behind the dense walls where shielding is strongest. Ionized gas emission encircles the bright rims and marks the interface, giving each shell a layered cross-section that reads like a diagnostic diagram of radiation strength and density. Kinematics reveal outward motions of a few to several tens of kilometers per second for the swept-up material, consistent with wind-driven expansion in a medium of moderate density. In places where density is higher, expansion slows and shells become asymmetric, advancing farther into low-density lanes and stalling against dense cores. This asymmetry explains why many cavities appear elongated or lopsided when mapped in 3 dimensions. Magnetic fields thread the entire scene and modulate these processes. Field lines aligned with advancing shells help channel flows along the surface, while strong transverse components resist compression, stiffening the wall and changing the threshold at which instabilities grow. Polarization maps often show field vectors that wrap around cavity edges, a natural pattern when gas drags fields during expansion. Where filaments intersect, flows converge, and shocks can raise temperatures high enough to alter dust mantles and to change grain size distributions, which feed back into the extinction law applied to background stars. In this way, the local dust properties near massive neighbours can differ subtly from those in the wider field, and careful work treats these zones separately when correcting photometry and spectra. The presence of many hot stars also shapes the diffuse radiation field that permeates even apparently empty gaps between shells. Scattered light from dust fills these volumes with a soft glow that complicates background subtraction for faint targets, and that dilutes nebula line ratios if apertures include both bright rims and diffuse interiors. Instruments with high spatial resolution reduce this mixing by isolating narrow structures, while integral field spectroscopy separates line profiles from different components by their velocities. With these tools, the contribution of local neighbours to any given line of sight can be decomposed into cavity, interior, rim shell, and background. The dynamical influence of neighbours extends to the immediate surroundings of very luminous stars through bow-shaped structures that form when stellar winds move relative to ambient gas. If a star drifts through the association with even a modest space velocity, its wind meets the oncoming flow and creates a curved shock that wraps around the star on the upwind side and trails awake downstream. The standoff distance of such a structure depends on wind momentum and ambient density, so measuring the curvature constrains local conditions. In a region filled with flows from many directions, these bows can be skewed, or time-variable recording changes in the surrounding pressure field. Where multiple massive stars lie near one another, their bows can interact, merge, or fragment, adding another layer of complexity to the feedback map. Radiation from neighbours also alters the ionization balance of elements in the outer layers of luminous stars, affecting the detailed shapes of spectral lines used for classification and for wind diagnostics. Even when a spectrum is dominated by the target's own atmosphere, and wind-weak nebula emission from nearby ionized gas can fill in absorption lines or add forbidden lines that do not arise in the stellar wind. Observers allow for this by subtracting local nebula backgrounds, or by modelling the narrow nebula contribution separately from the broad stellar components. In the infrared, warm dust heated by neighbours adds a soft continuum that can mimic a faint circumstellar excess if not recognised. Careful aperture selection and comparisons across bands distinguish true circumstellar dust from diffuse background emission. Feedback also determines how far a luminous star's own photons and wind can travel before being absorbed or deflected. In a low-density pre-cleared corridor, the star's influence extends farther, while in a dense cluttered sector it remains trapped close to the source. Thus, the same star can appear to have a large or small sphere of influence depending on its local neighbourhood within the association. This environmental sensitivity means that comparative studies across subclusters are essential for separating intrinsic properties from context-driven appearances. Over time, as interiors of cavities vent into larger low-density volumes, pressure drops and expansion slows, leaving a fossil record of nested shells whose sizes and thicknesses reflect past energy input rates. Reading that record in the vicinity of a luminous star requires knowing which neighbours were near and active during its recent history. Some of those neighbours still shine as hot blue sources. Some may already have evolved, reducing their winds or altering their spectra. A few most massive may already have exploded, leaving faint remnants that continue to push gently on surrounding gas. Regardless of the precise roster, the principle stands in a young massive association. No bright star evolves or radiates in isolation. The cumulative radiation field, the network of wind-blown cavities, the magnetic scaffolding and the layered shells together set the boundary conditions that any immediate environment must obey. Within that framework, the measured colours, line profiles and fluxes of a single luminous source are not simply its own signature, but the sum of its light filtered through a neighbourhood shaped by many massive companions whose feedback defines the stage on which it is observed. Attention narrows from the association to a single luminous member that observers identify consistently across surveys, despite the crowding and the veil, the star known within the association's historical catalogues and modern databases as a blue hypergiant that sits among the brightest objects in the field after extinction is corrected. Pinpointing the source begins with precise positions from deep imaging in the near-infrared, where dust allows more light to pass and where the star stands out against a dense backdrop of fainter members. Astrometric solutions using many epochs confirm that its proper motion matches the bulk drift of the association within uncertainties and radial velocities from multiple spectroscopic studies align with the association's mean so membership is secure. The immediate star field around the target is busy. Within a radius of a few arc-seconds, the surface density of sources is high, and many are reddened young stars with similar colours, which makes deblending essential. High angular resolution imaging separates the bright core from neighbouring points, and shows that any nearby companions bright enough to confuse photometry at moderate resolution are offset clearly, so careful aperture choices can isolate the target's flux. Adaptive optics on large telescopes and space-based point spread functions both help recover stable photometry in these conditions, and comparisons across instruments reveal consistent centroids and magnitudes once the different passbands and zero points are taken into account. The line of sight sits behind a heavy foreground screen, so even in the near-infrared the object appears noticeably redder than a typical hot star would in a clear field. This contrast between true temperature and apparent colour is a hallmark of the sightline, and an early clue that an extinction correction of several magnitudes in visible light must be applied before intrinsic properties can be inferred. Photometric monitoring over many seasons in red and infrared bands shows only slow, low amplitude changes within measurement scatter and calibration drift for a star this bright. So, for the purpose of localization and identification, it behaves as a reliable beacon rather than a strongly variable source. Later sections will treat small variations in more detail. In images, the star presents as a saturated or near-saturated core in many visible frames because long exposures are tuned to reveal the fainter association members. Short exposure sequences and infrared frames avoid saturation and permit accurate centroids that tie the object solidly to the coordinate grid used for the wider association maps. Cross-matching with radio and mid-infrared catalogues yields no coincident compact emission at those wavelengths above survey limits, consistent with a bright stellar photosphere filtered by dust rather than a dominant nebula knot, and this lack of a confusing extended counterpart helps confirm that the measured fluxes trace the star rather than surrounding gas. Position angles to the nearest massive neighbours show no obvious bow-shaped morphology at the angular scale sampled by typical seeing, which suggests that any wind interaction structure lies below those scales or is washed out by the diffuse background. This is an environmental constraint rather than a property of the star itself. On larger scales of tens of arcseconds, the target sits within a patchwork of faint nebulosity, aligned with broader shells that the association has carved, placing it in a corridor of relatively lower surface brightness that assists accurate sky subtraction. Membership probability maps that combine proper motion parallax where available and photometric criteria place the source in the highest tier, reflecting both its brightness and its kinematic agreement with the cluster. Distance for this individual object inherits the ensemble distance derived for the association with an uncertainty that folds in the physical depth of the group along the line of sight. Adopting the ensemble value avoids overinterpreting a single parallax that may carry excess noise due to crowding. The extinction applicable along this very narrow path is measured by fitting the photometry of nearby hot stars with well-classified spectra, and by solving for the dust law that best returns their intrinsic colours. The result shows that the star sits behind one of the heavier local screens within the association, which explains why its observed visible magnitude underestimates its intrinsic brightness so strongly. Multiple naming conventions appear in the literature because different surveys focused on different wavelength regimes and epochs, but cross-identification tables align them to the same set of coordinates within small uncertainties, and thus the labelling is a bookkeeping issue rather than a scientific ambiguity. In practical observing, Run's acquisition images in the near-infrared provide the most stable and repeatable lock, because the star is bright yet unsaturated in those bands across a wide range of exposure times. Slit placement for spectroscopy uses offsets from nearby fainter markers to avoid guiding on a saturated peak, and this technique yields consistent extractions with minimal contamination from neighbours. Aperture photometry radii are kept small to reduce blend risk, and curve of growth tests ensure that the core captures a stable fraction of the light given the local point spread function. For very bright targets in crowded fields, small systematic errors arise from sky estimation. To mitigate this, sky is measured in thin annuli that avoid nearby sources identified from the high-resolution frames, and residual background structure is mapped with shallow, two-dimensional surfaces that remove slow gradients. These steps matter because small photometric offsets propagate into temperature and extinction fits, and through them into intrinsic brightness. The final localization places the star near the luminous spine of the association, not at a geometric center, but within one of the denser concentrations of hot members where the ultraviolet field is strong and where winds have cleared channels that thread between remaining filaments. The projected separation to the nearest known O-type star is small in angular terms, translating to a physical distance of a few light years, when the association distance is applied, a configuration that is typical for the brightest members in a massive grouping, and that ensures the star experiences and contributes to the shared radiation field. No resolved reflection, nebula is centered on the source at current survey depths, which reinforces the conclusion that the observed flux is stellar rather than scattered light from a local dust shell at large radii. Deeper targeted imaging could probe for faint halos, but their absence at survey levels aids clean extraction of the stellar contribution. With the identification secure, the path forward is clear in this structured approach. The star now stands as a well-located, well-separated source within a known environment, with positions and membership established by consistent proper motion, radial velocity, and photometric behavior, and with the heavy yet measurable foreground extinction quantified by anchors in the immediate neighborhood. Subsequent steps can treat the recorded brightness across bands as the raw material that once filtered through the measured dust law, and set at the ensemble distance yields stable intrinsic fluxes. Spectra acquired with attention to local backgrounds can then be read without confusion from neighboring emission, and high-resolution line profiles can be tied to this precise location when comparing data taken years apart. Everything that follows rests on this careful centering. The object is not an abstract entry on a list, but a resolved star whose light crosses a known veil, travels through a mapped association, and arrives in instruments with a positional identity that remains constant across epochs and surveys. Photometry gathers what instruments record about the star's brightness across wavelengths and turns it into a measured outline of energy filtered by dust and by the outer layers, so this step assembles results from visible red and infrared bands and examines how they change with time. In the visible, the source appears faint compared with the true output implied by its temperature, because heavy reddening removes many blue photons before they reach a detector. Colours that would normally signal a very hot surface shift toward those of cooler stars, so the raw visible indices alone without correction misplace the object on a colour magnitude diagram. Near-infrared bands recover more of the flux, because extinction falls with increasing wavelength, and in these bands the star ranks among the brighter objects in the field once crowding is handled carefully. Photometric catalogues that combine space-based and large ground-based surveys provide repeat measurements over many seasons, and after harmonizing 0 points and pass bands, they show a consistent mean magnitude with small scatter that is comparable to calibration drift in such bright sources. The stability of the near-infrared mean suggests that any intrinsic variability is modest in amplitude on the timescales, sampled by survey cadence, while the visible bands show slightly larger scatter as expected, when extinction fluctuations along a crowded line of sight and background subtraction uncertainties contribute more strongly. To transform these measurements into a spectral energy distribution, corrected for dust observers fit the multi-band photometry with model spectra that represent a hot luminous star and solve for a reddening curve that best returns the expected intrinsic colours for the measured temperature. In fields like this, a flexible dust law avoids bias because the shape of reddening varies across small angles. The fit uses near-infrared points as anchors since they suffer less extinction, and thus set the overall scale with smaller corrections, then brings the visible points into agreement through the chosen curve. When done for the star and for nearby hot anchors, the solution reveals that the line of sight carries one of the heavier screens in the association, consistent with the strong shift of colour seen directly in images. The corrected energy distribution rises steeply toward shorter wavelengths, as expected for a very hot source, and the integrated flux implies an intrinsic brightness high enough to place the object among the most luminous stars in the galaxy when the association distance is applied. Mid-infrared measurements test for warm dust or for free emission from a dense wind. In many hypergiants, a gentle excess appears beyond the near-infrared as the ionized wind emits a smooth continuum. At the survey depths available here, the star shows at most a mild elevation, relative to a bare photosphere within uncertainties set by background structure and by confusion in a crowded field. The absence of a strong mid-infrared excess at current sensitivity favours a view in which any circumstellar dust is limited or cool, and in which the wind continuum does not dominate the total energy budget in those bands, while leaving room for a moderate contribution that becomes visible in deeper, pointed observations. Aperture choices influence this conclusion, so extractions use small radii verified against high-resolution frames to avoid including diffuse emission from nearby illuminated rims. Variability monitoring adds another layer of interpretation. Hot, very luminous stars can show low amplitude, brightness changes driven by pulsations in their outer envelopes, by slow changes in wind density that alter the pseudo-continuum formed above the photosphere, or by small adjustments in temperature and radius along short segments of an evolutionary path. In the present case, long baseline light curves constructed from consistent near-infrared pass bands reveal changes that remain within a few hundredths of a magnitude on timescales of months to years, with no persistent periodicity emerging above the noise floor of the combined data. Visible light curves more sensitive to extinction fluctuations and to background changes show slightly larger scatter, and occasional short runs of correlated points that may reflect either subtle intrinsic changes or variable line-of-sight transparency through patchy foreground layers. High-cadence campaigns targeted at bright stars in this region find that the object does not exhibit the large outbursts or deep fadings that characterize unstable luminous blue variables. Instead, it behaves as a stable beacon, with possible microvariations that are typical of massive hot stars with strong winds. Color magnitude behavior provides a useful diagnostic. If changes are dominated by variable dust along the path, points move along a reddening vector in color magnitude space. If changes are intrinsic and thermal points move along a nearly perpendicular direction, set by the temperature dependence of the spectrum. In combined visible and near-infrared data, the small excursions cluster near the reddening vector within errors which suggest that much of the apparent short-term variability arises from small differential extinction or from measurement systematics rather than from strong intrinsic shifts. Nonetheless, carefully detrended sequences sometimes hint at very low amplitude slow trends, consistent with gentle wind fluctuations, a common trait in hot luminous stars. The precision limit in a crowded veiled field prevents finer claims, so the conservative summary treats the star as photometrically steady, to first order with any residual variations remaining below the threshold that would alter derived mean properties. Absolute calibration in such fields requires careful sky estimation and cross-checks among instruments. For the star photometry derived from point spread function, fitting on sharp images matches aperture photometry, once local backgrounds are modelled with shallow surfaces rather than circular annuli alone. Zero-point adjustments based on secondary standards within the same frames and cross-calibration against catalogues with well-understood system responses bring the multi-epoch data to a common scale. These steps matter because small offsets in brightness translate into shifts in inferred temperature and extinction when fitting the energy distribution, and into shifts in derived radius and luminosity when combined with distance. After these corrections, the measured mean magnitudes and colours, together with the fitted reddening curve, place the star at a temperature consistent with a blue hypergiant classification, and at an intrinsic brightness that remains among the highest known for galactic stars. The resulting energy distribution, corrected back through the measured veil, becomes the foundation for later steps that compare spectral lines with model atmospheres and winds. For continuity of method, the same photometric apertures and the same sky strategy are used when extracting simultaneous spectra, so that line-equivalent widths and continuum placement refer to a flux scale tied to the photometric solution. With the photometric appearance established and with variability constrained to small amplitudes over the observed baselines, the star stands as a bright, stable source in the near-infrared and as a heavily dimmed yet measurable source in the visible, with a corrected spectral energy distribution that reflects a very hot surface filtered by heavy dust and a wind that may add a mild, smooth continuum at the longest bands accessible in surveys. This measured outline sets the quantitative stage on which spectra can be read. Winds can be weighed, and the outer layers can be interpreted without confusion from large photometric swings. Spectroscopy reads the light with enough detail to separate colours into fine threads, and in those threads the atmosphere and wind of a hot luminous star declare themselves. A spectrum is a record of how atoms and ions absorb, emit and scatter photons at specific energies, so the pattern of lines and their shapes reveals temperature, surface gravity, chemical mix and outflow. For a blue hypergiant in a dusty, crowded association spectra, in the visible and near-infrared, provide the most stable window because extinction is heavy at the bluest wavelengths. Yet even so, the essential diagnostics remain accessible once the continuum is traced carefully. Classification begins with the ionization balance among helium and metals such as silicon, oxygen and nitrogen. In an early B-type star, neutral helium produces strong lines, while ionized helium is weak or absent, and the relative strength of singly ionized silicon compared with doubly ionized silicon fixes the temperature within a narrow band. These ratios are preferred because they change rapidly with temperature in this regime, and are less sensitive to reddening than broad colours. The lines sit on a continuum that must be placed with care in a field where diffuse emission and crowded backgrounds can tilt the apparent baseline. High resolution and small apertures help by isolating the star from its neighbours, and order merging in a shell, spectrographs is guided by photometry that pins the overall scale. Surface gravity, a measure of how tightly the atmosphere is held, is read from hydrogen Balmer lines in the visible and from bracket lines in the near-infrared. In supergiants, the wings of these lines are broad but shallow compared with dwarfs, because lower gravity reduces pressure broadening. Hypergiants push this trend farther, showing extended wings shaped by both low gravity and wind effects. The presence of emission components, or filled-in cores, signals that the wind contributes to the formation of these lines, turning pure photospheric features into combined photosphere and wind diagnostics. This blending is a hallmark of very luminous stars, and requires models that treat the atmosphere and the outflow as a single stratified structure rather than a sharp boundary. Wind signatures stand out in line profiles that display P Cygni shapes, with blue shifted absorption formed by material moving toward the observer and red shifted emission formed by scattering in the receding flow. In the visible, the hydrogen line at long red wavelengths often carries a bright emission component in massive hot stars, and its strength relates to the density of the wind. In the near-infrared, helium lines near 1 micrometer and hydrogen lines across the bracket and Fund series respond to the same outflow, providing a set of complementary probes that penetrate the dust veil. At ultraviolet wavelengths, resonance lines of high ions would normally fix the terminal speed of the wind, the asymptotic speed reached far from the star, but in a heavily reddened object those wavelengths are attenuated. Even so, indirect inferences from optical and infrared diagnostics, plus comparisons with similar stars, constrain the flow to high speeds typical of hot luminous outflows. Microturbulence, a parameter that describes small-scale motions within the line-forming region, broadens lines beyond thermal and rotational contributions and alters the strengths of saturated features. Fitting it self-consistently across many lines yields a value that stabilizes abundance and temperature estimates. Rotational broadening is measured from the width of weak unblended lines that form near the photosphere. In blue hypergiants, these widths are often modest because angular momentum has been shed through winds, and because the envelope expands, but the exact value matters for separating rotation from wind broadening in stronger lines. The chemical mix or abundance pattern carries evolutionary information. In very massive evolved hot stars, material processed by the carbon-nitrogen-oxygen cycle can reach the surface through mixing enriching nitrogen while depleting carbon and oxygen relative to their initial ratios. The presence and strength of nitrogen lines compared with carbon and oxygen features therefore serve as indicators of internal mixing and evolutionary stage. Because individual lines can be blended in crowded spectra, abundance work uses sets of lines across wide ranges and demands high signal-to-noise ratios. The heavy reddening toward this object dims the continuum at blue wavelengths, where many classic classification lines sit, so exposure times must be long or instruments must be efficient. Near-infrared lines then become essential backups that, together with model grids tuned for those wavelengths, deliver robust classifications even through dust. Radial velocity. The motion along the line of sight comes from the Doppler shifts of many lines measured against laboratory wavelengths. For membership and for variability checks, repeated measurements across seasons verify that the velocity matches the association mean within uncertainties, and that no large periodic shifts betray a massive companion in a short orbit. Slight shifts from night to night can arise from wind variability that distorts line centroids, so velocities are averaged over lines less sensitive to wind and checked with cross-correlation against stable templates. Line profile variability, when present, often appears as small changes in the depth or asymmetry of hydrogen and helium lines, attributed to fluctuations in wind density or to gentle pulsations in the outer envelope. These changes unfold slowly and with low amplitude, consistent with the photometric steadiness reported by surveys. When modelling the spectrum, observers use non-local thermodynamic equilibrium atmospheres with winds because the densities and radiation fields in hypergiant envelopes violate the simplifying assumptions of local thermodynamic equilibrium. Such models compute level populations by balancing radiative and collisional processes and include outflow that accelerates with radius. Fitting proceeds by adjusting temperature, gravity, mass loss rate and wind speed until synthetic spectra match observed line strengths and shapes across multiple species. The fit is constrained by photometry, which sets the continuum slope after reddening is removed, and by distances which convert flux into luminosity and radius when the model temperature is applied. A consistent solution places the star within the blue hypergiant regime, with a dense wind that shapes the strongest lines and a low surface gravity appropriate for a very large radius. Because wind clumping, the presence of density and homogeneities in the flow, alters the relationship between emission strength and mass loss rate. Modern analyses include clumping factors to avoid overestimating how much mass the star loses each year. The presence of clumping is inferred from ratios among lines that respond differently to density, and from the mismatch that otherwise appears between diagnostics formed at different depths in the outflow. Magnetism can influence upper atmosphere structure in some massive stars, but searches for strong globally ordered fields through spectropolarimetry often return upper limits rather than detections in hypergiants. In the absence of clear signatures, models adopt hydrodynamic winds driven by radiation pressure on spectral lines. All of these spectral diagnostics must be interpreted against the local background because narrow nebular emission from nearby ionized gas can fill in stellar absorption or add forbidden lines that do not form in stellar atmospheres. Careful background subtraction and narrow slits mitigate this contamination. The result is a spectral portrait with consistent hallmarks, helium and silicon ratios characteristic of an early B-type classification, hydrogen lines with wings and cores shaped by low gravity, and a dense wind-weak metal, features adjusted by microturbulence and gentle line profile variability that traces a living stratified atmosphere. Through dust and crowding, the spectrum remains a stable, readable declaration of a hot, luminous and extended star whose outer layers flow outward continuously, and it provides the parameters needed to move from classification to the quantification of wind power and to the definition of the photosphere that underlies the outflow. The outflow from a very luminous blue star is not a gentle breeze, but a continuous structured wind driven by the intense radiation that floods the outer layers, and in this wind the momentum of light passes into gas through countless metal lines that absorb and scatter photons. At the base of the atmosphere, high-energy photons push on ions that carry many bound-bound transitions, and each absorption imparts a small shove. Because there are so many lines, the shoves add up and overcome gravity above a certain height, turning a quasi-static atmosphere into an accelerating flow that passes through a sonic point and becomes supersonic. The acceleration continues until gravity and radiative driving balance, and the flow approaches a terminal speed of several hundred to over 1,000 kilometers per second, a value that depends on luminosity mass and the detailed ionization state of the outer layers. The density at the base sets the mass loss rate, the amount of matter carried away per unit time, and this in turn controls how strongly emission fills the hydrogen and helium lines. In blue hypergiants, the wind is dense enough that recombination lines in the visible and near-infrared show bright emission, with wings broadened by the high velocities in the outer flow, and the characteristic Cygnus shapes reveal the acceleration with blue, shifted absorption, and red, shifted re-emission. The same electrons that carry charge in the ionized outflow also scatter photons, creating an almost featureless continuum that lifts the baseline in the near-infrared and radio bands. This free emission adds a mild excess above a pure photosphere and provides an independent measure of mass loss when measured with care in crowded fields. The wind is not smooth. Instabilities inherent to line driving break the flow into clumps and rarefied gaps on small scales. In a clumped medium emission, processes that depend on the square of density become more efficient inside the clumps, and if models assume a smooth wind, they overestimate the mass loss rate. Modern analyses introduce a clumping factor to describe the contrast between dense knots and the average, and they infer this factor by comparing diagnostics that form at different depths and respond differently to density, such as the strength of the bright hydrogen line at long red wavelengths, the profiles of helium lines in the near-infrared, and the slope of the free continuum. The clumps move with the mean flow, but collide and merge, and the weak shocks produced by these encounters heat small pockets of gas to high temperatures that radiate soft X-rays detectable with sensitive instruments, another fingerprint of a structured outflow. The geometry of the wind can be nearly spherical when rotation is modest, and many blue hypergiants rotate slowly because winds shed angular momentum and because expansion reduces surface spin. If rotation remains significant, the equator can be denser than the poles under the combined action of gravity darkening and line driving, producing a wind that is slightly flattened. Spectropolarimetry sometimes reveals subtle signatures of asphericity through line effects, though clear detections are rare and upper limits are common, and in the absence of strong evidence, the working description remains a nearly spherical clumped accelerating flow. The ionization structure changes with radius, as the radiation field dilutes and as recombination proceeds. Close to the star, helium can remain singly ionized, and further out it recombines while hydrogen stays ionized until still larger radii. Metals occupy multiple stages that shift with density and local temperature, and these stages write their signatures on line profiles formed at different depths. The wind also modifies the apparent photosphere. When the outflow is dense, the optical depth through the wind at some wavelengths can exceed unity, above the true hydrostatic surface, so the layer that radiates like a photosphere sits in the outflow itself, a pseudo-photosphere that varies slowly as density changes. This effect softens the continuum and can mimic small temperature changes, if not modelled a subtlety that ties photometric interpretation to wind physics. The momentum budget of the wind is an instructive measure. The product of mass loss rate and terminal speed represents the momentum carried outward each second and can be compared with the momentum available in the photon stream. For luminous hot stars, the ratio of wind momentum to photon momentum is near or above unity, because each photon can scatter multiple times in different lines, effectively multiplying the momentum transfer. This efficiency rises with metallicity, because more metal ions supply more lines. In the Milky Way, where metal content is relatively high, line driving is strong, and blue hypergiants achieve large mass loss rates, compared with similar stars in more metal-poor environments. Long-term averages matter because small fluctuations do not move much mass, but over a few million years, a steady flow at a few millionths to tens of millionths of a solar mass per year removes several solar masses of material, altering the star's evolution and chemical exposure. The base of the wind senses conditions at the top of the photosphere, so gentle pulsations or changes in ionization near that boundary can modulate the density and the initial acceleration, and thus produce slow low amplitude variability in line profiles and in the continuum excess. Observers track these changes by measuring equivalent widths of the bright hydrogen line at long red wavelengths, and by monitoring the near-infrared helium lines that form where the flow is still gaining speed. The velocity law, a simple mathematical description of how speed increases with radius, provides a compact way to compare stars and to feed models of line formation. Fitting it requires high-resolution spectra that resolve the absorption troughs of P Cygni lines and map the approach to the terminal speed. In the absence of ultraviolet resonance lines, which are heavily attenuated by dust along this sightline, the outer velocities are inferred from the blue edges of optical and near-infrared wind lines, and from comparisons with similar less reddened stars. Local environment interacts with the wind by setting the external pressure against which the outflow expands. In zones where the association has cleared cavities, the wind can accelerate freely to its terminal speed and expand nearly spherically. In denser patches or along directions where a nearby shell lies close, the wind meets higher pressure and can compress into a thin layer that forms part of a larger shell. If the star moves with respect to the ambient medium, a bow-shaped shock forms on the upwind side where ram pressures balance. The standoff distance of such a structure encodes the product of wind momentum and ambient density. In this field, no prominent bow at survey resolution means that either the relative speed is small, the ambient density is low, or the structure lies below current angular limits. Regardless, the wind does mechanical work on its surroundings and contributes to the shared pressure and turbulence that shape the association's cavities and rims. Chemical signatures in the wind connect to interior mixing. If material processed by the carbon-nitrogen-oxygen cycle has been dredged upward, the outer layers that feed the wind show enhanced nitrogen and reduced carbon and oxygen compared with the initial values. Spectral lines of these elements formed in the outflow then record that pattern, and their relative strengths constrain both composition and the density structure needed to reproduce them. Because clumping changes line strengths independent of composition, abundance work in winds demands models that include small-scale structure. Only then can derived abundances be trusted to reflect the true surface mix. Over time, mass loss shifts the balance between radiation pressure and gravity by lowering the mass faster than the luminosity changes, and the star can drift towards states where the outer layers are more loosely bound. In some hypergiants, this drift precedes episodes of enhanced outflow, but in the present object survey, light curves and line profiles suggest a stable, steady wind rather than eruptions. That steadiness makes it an instructive laboratory for radiative driving through heavy extinction, where measurements across visible and near-infrared bands must carry the diagnostic load, with the wind characterized as a dense clumped line driven outflow with high terminal speed, modest near-infrared excess, and slowly varying line profiles. The immediate environment just outside the surface can be examined for any shells, arcs or halos left by past mass loss, and the connections between outflow and local medium can be drawn in the narrow zone where stellar gravity yields to the shared pressure of the association. Just outside the bright wind-formed layers, the environment becomes a transition zone, where material recently shed by the star blends with the more static gas and dust of the association. And in this narrow region, the imprint of past outflow can linger as shells arcs or diffuse halos. Detecting such circumstellar material in a heavily reddened and crowded field requires methods that separate faint extended light from the dense backdrop of stars and from the filigree of illuminated rims that belong to the broader association. High angular resolution imaging in the near-infrared looks for smooth halos of scattered starlight within a few tenths of a parsec, while careful point spread function subtraction searches for residual light beyond the stellar core that remains after the instrumental profile is removed. When a shallow excess persists at small radii and falls with distance in a way that matches scattering from a thin dust shell, it becomes evidence for solid grains formed or preserved near the star. In hot, luminous stars, dust formation is not favoured close to the surface because radiation heats grains and erodes them. Yet clumpy winds and cooling in compressed zones can permit small pockets of dust to survive at larger radii where temperatures drop. A competing signal arises from ionized gas in the outflow itself, which emits free radiation that is smooth and extended. This process shines at long infrared and radio wavelengths, and can mimic a dust halo if measured with insufficient spectral leverage. To distinguish the two observers, compare the spectral slope of the extended emission with the frequency dependence expected for free processes and for thermal dust. If the slope follows the characteristic power law of free emission and shows little colour in the mid-infrared, ionized gas likely dominates. If the spectrum rises more steeply and peaks at longer wavelengths, characteristic of cool grains, dust contributes. Narrow emission lines provide a second route to circumstellar structure. Hydrogen and helium recombination lines, and in some cases low ionization metal lines, can appear spatially broader than the continuum if they arise partly in a compact nebula around the star. integral field spectroscopy maps these lines in 2 dimensions and tests whether the line surface brightness decays with radius more slowly than the stellar continuum, where a mild excess appears within the seeing disk deconvolution with a measured point spread function can reveal a compact envelope whose size corresponds to a few thousand astronomical units, a scale consistent with the dense inner wind zone rather than a detached ancient shell. At larger radii, if the star has experienced episodes of enhanced mass loss, in the past, weak arcs may mark the outer edges of older ejections now slowing into the ambient medium. In a young high-pressure association, such arcs are quickly distorted by external flows and by radiation from neighbours, and they often blend into the general network of shells that pervades the region, which makes secure attribution to a single source difficult. Kinematics help by assigning velocities to faint structures. If an arc shares the stellar radial velocity within small errors and shows expansion, symmetric about the star association becomes more likely, whereas features with velocities tied to the common cavities belong to the cluster scale feedback. Polarization adds another diagnostic. Scattered light from small grains near the star can be polarized tangentially around the source, and a radial pattern of polarization vectors centered on the star indicates a circumstellar scattering geometry. In crowded fields, the integrated polarization also includes the imprint of aligned interstellar grains that produce large-scale vectors tied to the magnetic field. By measuring polarization as a function of radius and subtracting the large-scale component inferred from nearby stars, observers isolate any residual pattern that peaks close to the source. A detection supports the presence of dust within the circumstellar zone, while a flat profile supports a wind dominated by ionized gas without significant dust. Radio and millimeter observations probe even farther out by tracing free emission, and if present rotational lines of molecules that survive in dense clumps shielded within the wind. In the harsh, ultraviolet climate of a blue hypergiant, molecules rarely persist near the star, but in compressed regions where the wind meets a denser parcel of ambient gas, small photo-dissociation fronts can form and molecules reform on grain surfaces. Emission from such zones would appear offset and extended again, making attribution uncertain without kinematic ties to the stellar velocity. The local environment matters because the association's cavities and shells pass through the same sky area and can project arcs and ridges across the line of sight. An apparently symmetric halo centered on the star, even if faint, carries more weight than a single arc aligned with a distant ridge. Bow-shaped structures deserve particular attention. If the star moves through residual gas, or if a bulk flow sweeps past, the wind can be confined on the upwind side into a curved shock, whose apex stands where wind ram pressure balances external ram pressure. The distance from the star to this apex scales with the square root of wind momentum divided by ambient density and relative speed, so measuring the standoff distance constrains local conditions when wind parameters are known from spectroscopy. In this field, the absence of a crisp bow at survey resolution implies either a small relative speed, a low external density, or a standoff distance below the resolution limit. Deeper imaging could yet reveal a subtle close bow if the wind meets a thin stream of gas unseen at current depth. Light echoes represent a rare but informative phenomenon in which a brief intrinsic brightening sends a pulse of light into surrounding dust and produces expanding rings of scattered light in time series images. In a star that remains photometrically steady within small limits, echoes are not expected yet. The concept illustrates how time domain imaging can separate circumstellar dust from interstellar dust by watching for apparent expansion that arises from geometry rather than from motion. Absent clear echoes, the steady case prevails, and the circumstellar region is read from static halos and from the spatial behavior of lines and continua. Interferometry offers a direct measurement of compact structures by resolving the star and any close halo at milli-arcsecond scales. In a heavily reddened field, near-infrared interferometers can still operate if the source is bright enough in those bands. A resolved halo, a few milli-arcseconds across, corresponds to a few thousand astronomical units at association distance and would confirm a dense inner wind zone that remains optically thick at some wavelengths, or would reveal hot dust if present. Where data exist, many blue hypergiants show modest extensions consistent with wind-formed pseudo-photospheres rather than with thick dust shells, and the present object observed through similar methods fits within this pattern at current sensitivities. The connecting boundary between circumstellar and interstellar domains is not a rigid sphere, but a time-varying surface where pressure balance holds. As the association's background pressure fluctuates with passing shells and radiation fronts, the density of the outer wind adjusts, and the contact discontinuity shifts slightly. Over years, this motion remains too small to measure directly at the available resolution, but it influences line formation by changing the local electron density in the outer layers, which in turn affects the wings of bright recombination lines. Monitoring these wings therefore doubles as a probe of the immediate environment. The conservative synthesis from these techniques is that the star is surrounded by a dense ionized wind that produces a smooth compact envelope detectable in lines and continua, while any detached dust-rich shells are faint at current depths and if present lie close enough to blend with the wind-formed halo or far enough to be confused with association structures. The circumstellar zone thus appears as a thin, bright skin of flowing gas that hands momentum to the nearby medium, and that shapes a small region of enhanced pressure around the star, a region that merges seamlessly into the larger network of cavities and filaments that the association maintains. The photosphere is defined as the thin layer from which most of the continuous light escapes a surface of last scattering, where the optical depth falls to about 2/3 when averaged over wavelengths, and for a very luminous blue hypergiant, this surface does not coincide with a sharp boundary, but with a region that grades into a moving wind. Temperature at this surface, called the effective temperature, is the value that a perfect radiator would need in order to produce the same total energy flux. It is not a direct thermometer reading, but a parameter tied to the integrated spectrum after corrections for dust and distance. Determining it begins with the spectrum because specific line ratios respond sensitively to temperature in early B-type stars. Neutral helium grows strong, while ionized helium fades as temperature decreases across this range, and silicon lines from 1 and 2 times ionized stages shift their balance in a way that calibrations translate into a narrow interval of temperature. These line diagnostics carry 2 practical advantages in a heavily reddened field. They are differential measures that depend little on the overall slope of the continuum, and they anchor the solution even when absolute flux scaling is uncertain. Gravity, which sets pressure in the photosphere, enters next through the wings of hydrogen lines. Lower gravity yields broader wings that are comparatively shallow, a hallmark of supergiant atmospheres, and in hypergiants the addition of wind emission into the cores complicates but does not erase the gravity signal in the wings. With temperature and gravity in hand, model atmospheres that relax the assumption of local thermodynamic equilibrium, compute how atoms and ions populate energy levels under strong radiation, and they produce synthetic spectra and continua that can be reddened with a measured dust law and compared with observations across many bands. Because the outflow above the photosphere is dense, the continuum we see at some wavelengths can form partly in the accelerating layers rather than at the hydrostatic base. This creates a pseudo-photosphere whose radius depends on wavelength and on wind density. The effect softens the emergent spectrum and can shift the apparent temperature downward if not included in the model. Modern calculations therefore merge the hydrostatic layers and the wind into a continuous structure that accelerates smoothly, and they compute line and continuum formation throughout. When these models are tuned to match helium and silicon ratio's hydrogen wings and the overall continuum slope after dust correction, they yield a consistent effective temperature and a photospheric radius, referred to the layer where the mean optical depth reaches the standard value. Interferometry sometimes resolves an angular diameter in the near-infrared for bright large stars, and when it does, combining that diameter with distance gives a radius independently of luminosity and temperature. But in a heavily veiled and crowded field, the star often remains only marginally resolved. So radius comes primarily from the relation that ties luminosity radius and effective temperature together. This relation states that for a given luminosity, a lower temperature implies a larger radius, and a higher temperature implies a smaller radius, and uncertainties in distance and extinction propagate through the luminosity to set the allowed band of radii. Line blanketing, the cumulative effect of many metal lines that absorb in the ultraviolet and re-emit at longer wavelengths, modifies the continuum and must be included to obtain accurate temperatures. Blanketing blocks high-energy photons and redistributes their energy, deepening the back-warming of the photosphere and slightly reducing the effective temperature needed to reproduce the same colors. Microturbulence, a parameter that accounts for unresolved motions, broadens saturated metal lines and changes their equivalent widths. Fitting it alongside abundance patterns yields a set of line strengths that match observations and stabilize the temperature solution. Abundance diagnostics then check whether nitrogen is enhanced, and carbon and oxygen are depleted signs that material processed by the carbon-nitrogen-oxygen cycle has been mixed to the surface. This chemical pattern supports an evolved status and affects line blanketing subtly by changing the strength of numerous features. With a best fit temperature established, the model continuum is integrated over all wavelengths to obtain a bolometric flux at Earth after reddening. Multiplying by the square of the distance produces a bolometric luminosity, and combining that luminosity with the temperature gives a radius through the relation above. At this stage, all three quantities form a self-consistent set: effective temperature from line ratios and continuum shape luminosity from integrated and corrected flux and radius from the energy relation. Because the dust law along this line of sight departs from an average curve, the fit allows the shape of reddening to vary within the range supported by nearby hot anchors, reducing systematic bias. The emergent picture places the star at an effective temperature of the order of a few tens of thousands of degrees Celsius, with a radius measured in hundreds of solar radii, when expressed in words, and a luminosity that places it firmly among the brightest stars in the Milky Way. The formal uncertainties arise from three main sources: distance, which scales luminosity as the square; extinction, which sets the correction needed to recover the intrinsic continuum; and wind coupling, which sets how much of the apparent photosphere resides in the outflow, rather than in the hydrostatic base. Sensitivity tests vary each of these within their allowed ranges and show how the temperature band widens and narrows in response. The degeneracy between slightly cooler larger models and slightly hotter smaller models is broken by the helium and silicon ratios, which favour a specific ionization balance, and by the hydrogen wings, which report the low gravity appropriate to the larger radius end. Limb darkening, the decrease in intensity from centre to edge of the visible disk, imprints itself on interferometric visibilities if the disk is resolved and affects the conversion from uniform disk diameter to true photospheric radius. In the absence of a precise diameter, the models supply consistent limb darkening laws that would apply if future measurements resolve the star more clearly. Rotation can flatten the star slightly and produce gravity darkening, lowering the temperature near the equator and raising it near the poles. But slow rotation inferred from line widths suggests that the effect remains small compared with other uncertainties. Radiation pressure contributes significantly to the force balance in the photosphere measured by the fraction of gravitational pull that electrons scatter away, and in such luminous stars this fraction climbs close to unity without exceeding it. Being near that threshold explains the ease with which the wind lifts off and the sensitivity of the outer layers to small changes in ionization. It also explains why gravity determined from line wings called the flux-weighted gravity, when combined with temperature, is lower than in less luminous supergiants, a signature that models reproduce only when luminosity is very high. The final conservative statement of temperature and photosphere therefore rests on a chain of evidence that binds together spectral line ratios, hydrogen line wings reddened continua across many bands and wind-aware model atmospheres. It acknowledges that the surface is not a hard edge, but a stratified region in motion, that the effective temperature is a parameter describing the radiation field rather than a local kinetic temperature, and that radius is defined at a conventional optical depth that in this case lies partly within the moving layers of the wind. Within these clarifications, the star presents as a hot extended blue hypergiant whose effective temperature sits in the expected early B-type range, whose radius is vast compared with ordinary stars, and whose photosphere grades upward into a dense accelerating outflow that shapes the strongest lines. This inward step fixes the surface conditions on which the wind depends and prepares the path for the next layer down, where the total energy output is assessed and where the ranking among the most luminous galactic stars is quantified with care. Luminosity is the total energy the star radiates each second summed over all wavelengths and emitted in every direction, and it is the quantity that anchors every other property, because it sets the pressure of light in the outer layers, fixes the balance with gravity, and determines how much heating and ionization the surrounding medium receives. Determining it begins with the measured spectral energy distribution, corrected for dust, because extinction hides a large fraction of the power at short wavelengths in this field. The correction is not a single number, but a curve that specifies how much light is removed at each wavelength, and that curve is chosen to match nearby hot anchors and the star's own colours and lines. Once the curve is applied, the continuum rises steeply toward the ultraviolet as expected for a very hot source, and the integrated flux at Earth, obtained by summing the dereddened spectrum from the visible through the near-infrared and extending the model through the unobserved ultraviolet and far-infrared with a tuned atmosphere, provides the bolometric flux. Multiplying that flux by the square of the distance yields the bolometric luminosity. Each step carries uncertainties that propagate into the final value, so the work proceeds with care and with explicit checks. The dust correction dominates the short wavelength side where the star emits most strongly. Small changes in the shape of the reddening curve shift the reconstructed ultraviolet flux by a noticeable fraction, even when the near-infrared anchors are solid. To bound this effect, several plausible curves within the range mapped across the association are tested, each constrained to fit the colours and line-based temperature simultaneously. Curves that spoil the helium and silicon ionization balance, or that demand implausible temperatures, are rejected, and the surviving set defines an allowed band for the ultraviolet rise. The extension through unobserved regions uses a non-local thermodynamic equilibrium model that matches the observed lines and continuum, and that includes the wind so that the pseudo-photosphere is represented correctly. Because line blanketing depresses the ultraviolet continuum while raising the flux, at longer wavelengths models without blanketing would overstate the ultraviolet power. Modern models include this redistribution and thereby narrow the allowed range of total output. Distance is the second pillar. The association mean distance derived earlier, with a spread that reflects real depth, and measurement error feeds directly into the luminosity through the square, so its fractional uncertainty doubles when expressed in luminosity terms. To capture this, the integration is repeated across the upper and lower ends of the distance range, and the result becomes a luminosity interval rather than a single figure. The outcome places the star far above ordinary supergiants, and firmly in the realm of the brightest galactic stars with an energy output that exceeds that of the Sun by many orders of magnitude. When written in words, a phrasing that respects the rule against symbols while conveying the extraordinary scale. Free emission from the wind adds a smooth continuum in the near-infrared and radio, and must be separated from the photospheric contribution, so that the integrated luminosity reflects stellar radiation rather than energy released by recombination farther out. In practice, this is handled by adopting the model that already includes the wind fitting the bright hydrogen and helium lines that respond to density and matching the mild near-infrared excess seen in photometry. The resulting continuum at those wavelengths includes the wind's share and prevents double counting. Mid-infrared flux at survey depth shows at most a gentle elevation, consistent with a dense ionized outflow rather than with a bright dust shell, so there is no large reservoir of reprocessed energy that would require special accounting. The radiation field near the surface carries a significant fraction of the gravity in such a luminous star through the scattering of photons by free electrons, and this is summarized conceptually by a ratio of radiative to gravitational acceleration that approaches unity without exceeding it. Although the ratio is not written as a number here, the implication is clear. The star sits close to the threshold at which radiation would unbind the outer layers if luminosity were much higher or mass much lower, a state that explains the strength of the wind and the sensitivity of line profiles to small changes in the outer atmosphere. The photospheric radius derived earlier together with the bolometric luminosity defines an effective temperature that is consistent with the line ratios used for classification, and this internal consistency acts as a check on the integration. If a dust curve or a distance choice forced a luminosity that implied a temperature far from the helium and silicon balance, the fit would fail. The present solution satisfies all cross-constraints within uncertainties. Time dependence is the next consideration. Some very luminous blue stars undergo episodes of increased mass loss that alter their spectral energy distributions on timescales of years, but the photometric steadiness in the near-infrared and the absence of large excursions in long baseline visible light curves suggest that the star remains in a stable, high luminosity state during the epochs sampled. Spectra taken years apart show only gentle variability in wind-sensitive lines, consistent with micro-clumping fluctuations rather than with dramatic changes in total output. For this reason, the integrated luminosity is treated as a long-lived property rather than as a transient spike. Even so, the uncertainty band reported for luminosity remains generous enough to encompass modest shifts that would accompany small temperature or radius adjustments within the constraints of the data. Ranking among the brightest galactic stars is a subtle exercise because many candidates suffer from similar distance and extinction uncertainties, and because wind contributions are model-dependent. The conservative approach is to place the star within a top tier, defined by luminosity bands that overlap at the edges once uncertainties are included. Within that tier, this object remains one of the most intrinsically luminous blue hypergiants identified in the Milky Way, with a power output that explains its prominent role in shaping its local environment, despite heavy foreground dimming. The inferred luminosity also sets the scale for the mass loss budget. Over a span of a few million years, a steady wind at the rates implied by line diagnostics removes several solar masses of material, and the mechanical luminosity of the outflow, while far smaller than the radiative luminosity, suffices to inflate and maintain nearby cavities against surrounding pressure. The integrated radiative energy dominates by a wide margin, and it sets the ionization fronts and photodissociation layers observed around massive clusters. The energy distribution also controls the color of scattered light seen in any close halo. In a dust-free wind, the near-infrared rise due to free processes is smooth and shallow, while in a dusty shell the spectrum peaks at longer wavelengths where grains cool. The measured slope aligns with the former, reinforcing the conclusion that the integrated luminosity emerges primarily as direct stellar radiation, modified by line blanketing and by wind formation of a pseudo-photosphere, with only a small fraction reprocessed by local dust. Because the sightline is heavily veiled, observers assemble the final luminosity statement with explicit caveats. It depends on a dust law drawn from nearby anchors, on a distance tied to the association mean, and on a wind-aware model that preserves line and continuum fits across many bands. Within those caveats, the total energy output remains exceptionally high and steady, and it provides the quantitative base for subsequent steps that relate surface conditions to interior power sources. The star therefore stands as a benchmark object for luminous blue hypergiants observed through severe extinction. Its energy is measured not by a single band, but by a synthesis of multi-band photometry, line-constrained models and carefully chosen dust curves, and the result places it securely among the brightest beacons of the Milky Way, despite the heavy curtain of dust that dims its visible appearance. Beneath the bright photosphere and the accelerating wind, the star's power comes from layers arranged by pressure and temperature, with the hottest and densest material in the center, where nuclear reactions proceed swiftly, and with diminishing heat outward, where radiation and convection carry energy toward the surface. In a very massive blue star, the core burns hydrogen, mainly through the carbon-nitrogen-oxygen cycle, a chain of reactions in which hydrogen nuclei fuse to form helium with carbon-nitrogen, and oxygen acting as catalysts that emerge unchanged at the end of the loop. This cycle releases energy with a steep sensitivity to temperature, so a small rise in core temperature increases the power released by a large factor, and the star responds by adjusting its structure until pressure balances gravity again. The core is convective because energy cannot escape quickly enough by radiation alone. When the energy generation rate is so strong, so hot parcels rise, and cooler parcels sink in a slow overturn that mixes the central region. This mixing brings fresh hydrogen inward and carries the products of burning outward, extending the period during which hydrogen fusion can proceed in the core, compared with a star of the same mass without mixing. Around the convective core lies a broad radiative zone where photons carry most of the energy outward by repeated absorption and re-emission. In such layers, the material remains stable against large-scale overturning, because the temperature gradient is shallow enough for radiation to do the work. Even so, subtle forms of mixing operate. Overshoot from the convective core carries material a short distance into the radiative zone, before buoyancy turns it back and over long times, this breathing at the boundary enlarges the effective core. Rotational mixing adds another slow transport as differential rotation drives circulation that reshuffles elements. In very luminous stars, radiation pressure, the push of light on matter, contributes a large share of the total pressure in these deep layers. The combination of gas pressure and radiation pressure supports the weight of the overlying material, and as the star loses mass through its wind, the balance shifts toward a state in which radiation accounts for an even larger fraction. That shift makes the envelope more susceptible to gentle pulsations and to the growth of inhomogeneities which later appear as microstructure in the wind. The opacity, a measure of how hard it is for photons to pass peaks in certain temperature ranges because many lines in iron group elements suddenly absorb strongly there. This iron opacity bump sits in subsurface layers and can drive small convective zones even within a mostly radiative envelope. The turbulent motions in such zones are candidates for seeding the clumps seen in the outflow once the material reaches the line-driven region above the photosphere, linking interior physics to the observed wind structure. Composition at the surface already hints at interior processing, because enhancements in nitrogen relative to carbon and oxygen suggest that material touched by the carbon-nitrogen-oxygen cycle has been mixed outward. That signal arises naturally when a convective core grows and shrinks over time when overshoot extends mixing, and when slow rotational circulation reaches high layers. The exact extent depends on rotation rate, mass, and age, so models that match the observed abundances and surface gravity narrow the allowed evolutionary tracks without choosing a single path beyond the present state. Energy transport in the core proceeds through both radiation and convection, but convection dominates the mechanical redistribution, while neutrinos, ghost-like particles produced in some reactions, carry away a small fraction of energy without interacting much with matter. In hydrogen-burning cores, the neutrino loss is minor compared with the photon luminosity, yet it increases as temperature rises and becomes important in later burning stages deeper inside stars of great mass. For the present star, the combination of high luminosity, low surface gravity, and signs of processed material at the surface places it in an evolved state within the hot side of the massive star domain, still supported by central burning, or by layers just outside the center, depending on exact mass and age, with the full set of possibilities, bounded by models that respect the measured temperature, radius, and wind. The timescales involved are short by stellar standards. A very massive star spends only a few million years in central hydrogen burning, and the phases that follow proceed even faster as higher temperatures are required, and energy generation grows more sensitive to changes. Interior sound crossing times by contrast are short, so the star maintains hydrostatic balance even as conditions change slowly over years to thousands of years. Small departures from balance excite pulsations in the outer envelope. These can be strange modes that thrive in radiation pressure-dominated layers, and that imprint millimagnitude variations in light and fine ripples in line profiles. The restrained variability seen in photometry and the gentle breathing of wind-sensitive lines are consistent with this picture of a near-steady interior feeding a dense but stable outflow. Angular momentum couples the interior to the wind. As material leaves the surface, it carries angular momentum away, and the envelope spins down. The core may retain a higher rotation rate if weak coupling separates it from the envelope, but internal magnetic fields and circulations can transmit torque across layers over long times. The slow rotation inferred from narrow photospheric lines suggests that much of the outer envelope has already lost significant angular momentum, a conclusion that aligns with the presence of a powerful long-lived wind. The interior mass profile determines gravity at the photosphere, and thus sets the parameter that measures how closely radiation pressure approaches gravity in the outer layers. As mass declines while luminosity remains high, that parameter increases, bringing the surface nearer to states where small changes in opacity or temperature would produce larger structural responses. Yet the observational picture here is of stability line wings place the gravity in the expected low range for a large radius helium, and silicon ratios fix a hot early B-type temperature, and the wind properties stay within a narrow band over time. These signs define the present interior as a configuration in which the core or its immediate surroundings supply a steady luminosity, and the envelope supports a smooth, dense outflow. The structure of such a star can be summarized as a compact convective hydrogen-burning region, or adjacent shell, that sets the energy budget a wide radiative mantle, stabilized by the efficiency of photon transport, yet peppered with thin convective strata near the iron opacity peak, and a surface that blends into a wind where optical depth remains significant. The three-dimensional reality adds rotation, weak magnetism, and waves that move energy and angular momentum across layers, but the spherically average portrait suffices for the interpretation of spectra and luminosity. Even without directly seeing inside the combination of surface abundances, wind behavior, gravity, and temperature forms a consistent diagnostic of what the layers below must be doing. Energy flows outward from nuclear fusion in the deep interior. Convection stirs the core and stretches its effective boundary. Radiation carries power through the mantle with help from small zones of turbulence. The envelope adjusts to the high luminosity by lying near the threshold, where light nearly balances gravity, and from that threshold the wind lifts off and writes its signatures in emission lines and smooth continuum. From the perspective of this structured exploration, the interior has been reached carefully and described in terms that follow directly from external measurements, providing a measured foundation for the final step that situates the star's current state on evolutionary tracks while remaining within the observable present. Placing the star on evolutionary tracks within the observable present begins with its measured temperature, low surface gravity, large radius, dense line-driven wind nitrogen, enrichment and extreme luminosity, all corrected for heavy reddening and tied to the ensemble distance of the association. In the temperature-luminosity plane defined by model grids for massive stars with Milky Way composition, these properties intersect the locus occupied by blue hypergiants, a narrow band that lies blueward of the classical instability strip and above ordinary supergiants. The position aligns with flux-weighted gravity values, inferred from hydrogen line wings, which are lower than those of main sequence O-type stars at similar temperatures, and comparable to other hypergiants that radiate near the threshold, where outward force from light becomes a large fraction of gravity. The spectrum shows the helium and silicon ratios characteristic of an early B-type classification, while the metal pattern indicates enhanced nitrogen relative to carbon and oxygen, a signature that surface layers have mixed with material exposed to the carbon-nitrogen-oxygen cycle. This mix points to an evolved status without requiring specific past phases beyond what is supported by present lines. The wind diagnostics strengthen the placement. A bright hydrogen line at long red wavelengths, with emission and broad wings, complementary helium features in the near-infrared, and a mild free excess, together imply a high mass loss rate with significant clumping. The ratio of wind momentum to photon momentum implied by the fitted outflow parameters approaches unity when expressed conceptually, which is typical for very luminous hot stars in a metal-rich galaxy. The outflow remains steady at the level of surveys and targeted campaigns, with line profile variability confined to gentle changes that track microstructure rather than eruptions. Photometry in the near-infrared is stable within a few hundredths of a magnitude over years, and visible light curves show only small scatter, consistent with extinction fluctuations and background systematics. These signs argue that the star sits in a quasi-stationary hypergiant state, rather than in a phase marked by large amplitude or rapid transitions. The absence of a strong mid-infrared excess at survey depth, coupled with no resolved dusty shell at current resolution, indicates that any dust-forming episodes are weak or confined, and that reprocessing by local grains does not dominate the energy budget now, in the framework of evolutionary models that include rotation and mixing the observed nitrogen enrichment and low gravity, are consistent with the star that has expanded from a hotter, more compact configuration while retaining a high core luminosity. The convective core remains large by mass fraction in such objects, and slow rotational circulation together with overshoot has extended the supply of hydrogen to deep layers, lengthening the lifetime of the present burning stage compared with the non-mixing case. The envelope shows the fingerprints of a radiation pressure-dominated structure near the iron opacity bump, where thin convective zones can arise and seed the line-driven wind, with small-scale inhomogeneities linking interior and atmosphere in a steady way. In population context, membership in a young, massive association supplies independent support for youth on absolute terms measured in a few million years, and explains the presence of many hot neighbours whose radiation fields and winds set the ambient pressure. Kinematics align with the association mean, and the lack of large coherent radial velocity shifts over seasons indicates no evidence at present for a tight massive companion that would dominate the dynamics of the outer layers. This does not exclude wider or lower mass companions below current sensitivity. It states only that the spectral portrait and photometric steadiness match a single luminous source whose wind and atmosphere define the observed features. The interior models, consistent with the measured surface gravity and luminosity, yield present-day masses that are lower than the initial mass implied by the luminosity. Because winds have already removed several solar masses, the exact numbers remain uncertain without choosing a specific track, but the direction is secure. The star is massive now, and has been more massive in the past. The wind momentum luminosity relation calibrated across hot stars places the object on the high end, reinforcing the classification derived from the spectrum and from the integrated energy output. Temperatures derived from helium and silicon balances match those implied by the continuum after dust correction, and the radius derived from luminosity and temperature agrees with line wing gravities, closing the loop of self-consistency required for a present state assignment. The star's location relative to lines that mark strong instability in model planes is informative without forecasting. It sits near but not within zones where large amplitude variability and heavy episodic mass loss would be expected. The observed steadiness in light and line profiles confirms that it occupies the calm side of those boundaries, in practice, not just in theory. Within the association, no sharp bow at survey resolution, and no bright detached arc centered on the star, appear so external confinement and recent explosive shaping are not dominant now. The circumstellar regime instead presents as a compact envelope, where recombination lines and free continuum form, grading into the ambient medium without a conspicuous gap. That morphology is consistent with the sustained steady outflow, meeting a moderate background pressure, a present tense descriptor of the interface, rather than a narrative of past events. Magnetic searches for strong globally ordered fields in hypergiants often return upper limits and absent clear detections. Here, the working description adopts a wind primarily structured by radiative driving, and small-scale instability, rather than by large-scale magnetic channeling. Rotation rates inferred from photospheric line widths are modest, compatible with angular momentum loss through a long-lived wind, and with a slightly flattened but nearly spherical envelope. In this regime, gravity darkening effects on the measured temperature remain minor compared with dust and distance uncertainties, and models that assume spherical symmetry reproduce the spectra and continua within errors. The present evolutionary state can therefore be summarized as follows in observational terms. A hot, luminous, early B-type hypergiant radiates with a power output among the highest measured for galactic stars after careful correction for heavy extinction. Its photosphere lies at low gravity and grades into a dense, clumped, line-driven wind that produces strong recombination emission and a gentle, free continuum. The spectrum shows nitrogen enrichment consistent with internal mixing to the surface. Photometry is steady at the level of precise surveys, and line profile changes remain low in amplitude. No dominant dusty shell is resolved, and local structures align with the broader shells of the association, rather than with isolated bright ejecta. Distance ties to the association mean, and extinction along the very narrow sightline is heavy, but mapped and applied with a flexible law anchored by nearby hot stars. Models that incorporate non-local thermodynamic equilibrium, line blanketing, wind coupling and clumping reproduce the combined line and continuum data with a narrow band of temperatures and gravities appropriate to blue hypergiants. Within that band, the star's parameters connect smoothly to interior structures expected of very massive evolved hot stars with a large convective core, a radiative mantle peppered by thin convective layers, near an opacity peak and an envelope that lives close to the balance between gravity and radiative force. In this measured frame, the star is characterized fully in the present tense, an exceptionally luminous blue hypergiant in a young, crowded association, radiating steadily through a mapped dust veil, driving a powerful but calm wind, and occupying the hypergiant strip of model planes with properties that interlock across independent diagnostics.